Hello, everyone, and welcome to Lecture 16 of GPU Computing. Today, we're going to talk about sparse matrix computation, and in fact, we're going to have two parts of this topic. Today, we're going to look at two particular storage formats when computing sparse matrices, COO and CSR, and next time we're going to look at other formats that allow us to do other things. So what we will look at today, like I said, the parallel pattern we're looking at is sparse matrix computation. Now, there are a lot of different things that we do with sparse matrices. What we will be focusing on to showcase some of the challenges that we face when we do sparse matrix computations, we'll be focusing on one case study, which is sparse matrix vector multiplication, or SPMV. There's all kinds of other things we do with sparse matrices, but we don't have, we can spend a whole course on that, but we don't have enough time for that. So we'll only be doing two lectures on sparse matrix computations, and during these two lectures, we'll be focusing on sparse matrix vector multiplication as our case study. We'll also be looking at multiple storage formats, and I'll explain what those are later on. But today, we're going to focus on two storage formats, the coordinate format, or COO, and the compressed sparse row format, or CSR. And next time, we will look at two other formats in which we will kind of see how we can how the choice of storage format impacts how we process sparse matrices. Okay, so let's get started. Before I talk about formats and SPMV, let's first talk about what is a sparse matrix. Now, a dense matrix is a matrix where the majority of the elements in the matrix are non-zero, and here I'm using blue to indicate that some element has a non-zero value there. So we say that a matrix is dense when the majority of the elements in that matrix are non-zero. In contrast, we say that a matrix is sparse when many of the elements in the matrix are zero. Okay, so if a matrix has many different zeros, many zeros inside of it, then we say this matrix is sparse. And it turns out that a lot of real-world systems are actually sparse. A lot of the matrices that we use whenever we're doing all kinds of computations turn out to actually be sparse, and they turn out to actually be very sparse. So the vast majority of elements in a lot of matrices that we use out there are actually zeros. And the fact that these matrices are zeros means that when we do things with these matrices, like multiply them with vectors or multiply them with other matrices, we can take advantage of the fact that we have all these zeros to save on multiple things. So what are the things we can save on when we take advantage of the fact that the matrix has many zeros? Well, there's several opportunities. First, we can save memory, okay? Because if a matrix has a lot of zeros, okay, we can save memory by compressing the matrix such that we only store the non-zero values and we don't store the zero values. So we don't need to allocate space for the zeros, and this allows us to save memory, okay? Or even storage. If we're storing the matrix in a file, we can save storage, okay? Now, when we don't store these zeros anywhere and we save memory, there's also a kind of an effect of that. And the effect of that is that when we compute with this matrix, the fact that we don't store these zeros means we don't need to load these zeros when we are computing, and this helps us save memory bandwidth. And it also means we don't need to compute with these zeros, which also saves computation time. So when I take a matrix and multiply it with a vector, another vector, or another matrix, okay, I have to go through all these non-zeros and process them when I'm doing the matrix vector or the matrix multiplication. But when my matrix has a whole bunch of zeros inside of it, not only do I not need to store these zeros, which helps me save memory, I also don't need to load and compute with these zeros, which saves the memory bandwidth and the computation time. Okay, so when we look at sparse matrices, we spend a lot of time thinking about how can we represent sparse matrices in a way that allows me to save memory and also allows me to avoid loading and computing with zero values. So a lot of the work on sparse matrices has to deal with how to design different storage formats for these sparse matrices. So there's actually many storage formats for sparse matrices out there. What we will do is we will focus on 4 different storage formats in this lecture and the next lecture. And again, you can go into all kinds of other formats that allow you to optimize for all kinds of different things. But we will focus on these 4 because they're sufficient to kind of demonstrate all the concepts that we would like to demonstrate in an introduction to this kind of topic. So one format is the coordinate format. Another format is the compressed sparse row format, and these are the 2 formats we'll focus on today. Another format is the LPAC format, and the abbreviation for that is ELL. Coordinate format abbreviation is COO, and the compressed sparse row format is CSR. And then there's also the jagged diagonal storage format, which is also JDS. And there are many other formats again out there. There's still research on, people still do research on different formats for representing sparse matrices depending on what their specific application is. Somebody's asking how recent are these? These have been around for quite a while. The reason we look at them is they're kind of the classics, and particularly for GPU, they allow us to emphasize different things. A lot of the other formats are kind of squeezing more and more benefit out of these formats, but they rely on kind of similar principles. So yes, these formats are commonly used, and there are other formats that are also used. But hopefully, by covering these formats, you can easily go and read up on another format, understand why they made the decisions that they made. So thank you for that question. Okay, so different design, the reason we have different formats is because, as you can expect, different formats are good at different things. So there's various considerations that go into designing a storage format for sparse matrices. One of them is space efficiency. Okay, how efficient, how much memory do I save when I use this format? Okay. Another one is flexibility, and particularly here I mean the flexibility in terms of modifying the matrix. Okay, so some formats make it easier to add, reorder, or remove values than other formats. Okay, so if I plan to kind of modify my matrix a lot, I might choose a different format from if I'm planning to just keep my matrix fixed the whole time. My matrix is constant throughout my computation. Another one is accessibility. So the ease of finding the desired data. So when you access a matrix, you want to access it in a particular way. Maybe you want to go through all the rows of the matrix, or maybe you want to go through all the columns of the matrix. Okay, depending on how you would like to access your matrix, different formats might make certain types of accesses easier than others. Yet another one is the memory access pattern that the storage format enables, right? In the context of GPUs, it's whether this storage format enables memory coalescing. Okay, so the choice of storage format may impact, how you lay out your data impacts how you access your data, the memory access pattern. So you can design formats that give you better coalescing. And then finally, load balance. And the load balance means how much work each parallel worker has. And in the context of GPUs, this translates into control divergence. Okay, so how much does your format allow you to minimize control divergence? Okay, so these are the different considerations that go into designing sparse matrix storage formats. And by the way, some of these are kind of general. So space efficiency is, a general concept, but some of these are specific to a certain application, right? So, so the memory access pattern, the load balance. Well, when we talk about these, we talk about them in the context of a specific application. How these formats allow a specific application to have coalesced access speed. How these formats allow a specific application to minimize its control divergence. And for this reason, When we talk about these formats, we're going to talk about them in the context of a specific application, and that's SPMV, or sparse matrix vector multiplication. So the choice of the best format depends on the computation, okay? We will use sparse matrix vector multiplication, or SPMV, as an example to study the different formats. So in this lecture and the next lecture, we'll be looking at sparse matrix vector multiplication, which is where you take a sparse matrix and a dense vector, okay, and you produce a dense vector. This is what we will be looking at now and next time, okay? However, there's all kinds of other sparse matrix computations that you might want to do. Maybe you're doing sparse matrix with a sparse vector, or maybe you're doing a sparse matrix with a dense matrix, or maybe you're doing a sparse matrix with another sparse matrix. And there's a whole bunch of computations you can do with sparse matrices. And of course, different storage formats may be good for different computations. Okay, but we will use this particular computation as a case study just to showcase some of the challenges that go into dealing with sparse matrix computations. Okay. Okay, so let's start with the COO format. The COO format is as follows. Let's say I had this matrix over here. It's a sparse matrix. I have these white squares represent 0 values, and the non-white squares represent non-zero values. Okay, I'm using integers for simplicity, but obviously this matrix could have floating points, it could have doubles, it could have all kinds of data types. Now, the way that the coordinate format works is that we're going to store every non-zero along with its row index and its column index. Okay? So what we do is we take these values, these non-zero values in our matrix, we're going to put those in an array, one after the other. So we have 1, we have 7, we have 5, we have 3, right? We have 9, okay? And we put all the elements one after the other. And then for each element, we're going to have a row array and a column array that tell us for each element what the corresponding row and column index are. Okay? So what this does is it says that the value 1 is at row 0 and column 0. So here the value 1 here is at row 0 and column 0. The value 2, for example, is at row 2 and column 1. So here when we go to the value 2, we find that the value 2 is at row 2 and column 1. Okay, clear? Questions about this format? Someone's asking, is this similar to how we represent graphs? And yes, it is. It is similar to how we represent graphs. And in fact, after our 2 lectures on sparse matrices, we're actually going to have another 2 lectures on graphs. That's why I told you that you guys will be quite accustomed to these formats by the time we finish the sparse matrix and graph lectures in this course.
Doctor?
Okay. Yes.
When you say the matrix or whatever is in this format, do we have to, as a programmer, change our data that is stored in memory, change it to this format, or do we assume that our data is already this way? Like in practice, how is it done?
I mean, you could have libraries that will, you give them a dense matrix, and then they sparsify them for you, or they read some sparse matrix from a file and they provide them for you. But otherwise, you can also implement such a library yourself. Okay. So who converted the matrix to this format, whether it was you or whether it's some library that you called, is it's a detail. We don't care about that. But what we care about is what this format, how this format works and how we can use it to perform different kinds of sparse matrix computations.
Professor, depending on how sparse your matrix is, you could end up having more data in your COO than the original matrix.
Right. So if your matrix, this matrix here is quite dense, okay, just because I have, I can only fit such, I cannot fit a huge matrix on this slide. So you're right that, with a matrix this dense, you probably end up need more space to store the sparse matrix representation than you need to store the matrix as a dense matrix itself. However, when this matrix is thousands by thousands, then you can easily see how you quickly end up saving a lot of memory when you use the sparse matrix format. So yeah, good observation. You know, if your matrix is this dense, right, you probably don't want to make it sparse. If your matrix is 50% dense, or even 20% dense, or even 10% dense in some cases, you probably don't want to sparsify it. But sparse matrices in practice can be very sparse. We're looking at less than 1% of the elements are zeros, are non-zeros. Okay, so having seen the COO format, now the question is, or let's take a look at how we can use the COO format to perform SPMV, or sparse matrix vector multiplication. So let's say I have this sparse matrix, and what I would like to do is I would like to multiply this sparse matrix by this dense vector to produce this dense vector. Okay, and the question is, how can I, if I want to do this in series, it's easy, right? I just go through I can go through each element and multiply by the corresponding input value to get and update the corresponding output value. But if I want to do this in parallel, how can I do it?
The way we did it before, no?
Well, we haven't done sparse matrix vector multiplication before. We didn't even do dense matrix vector. We did dense matrix matrix. How can we do sparse? Go ahead.
Sorry. We have to put the threads on the value matrix.
You mean assign a thread to each one of these values?
And the value value array that below.
So you want to assign a thread to every what?
The value array تحت. We take which row and which column, and we add the sums in the output array and the output vector. Because we can do it the way we did it before in matrix multiplication, where we assigned a thread for each output element of the matrix. Because, right?
Okay, so why can't we do it? Why can't we assign a thread to each output value, for example?
I would argue we should, because some non-zero elements can now be some zero elements can now be non-zero.
Okay, so these are actually two very possible approaches to parallelizing this. We can assign a thread to every output value, okay, and have that thread compute multiply the row with the input vector to get the output value, or we can assign a thread to every non-zero value in the matrix and have that thread, okay, find the input that corresponds to that non-zero value. So in this case, it would be this, and then do the multiplication and update the corresponding output value. So both of these are possible ways of parallelizing it. What way seems most suitable for the COO format?
One
so
thread.
let's say, for example, that I assign a thread to every output element in this format, and that thread wanted to go through the corresponding input row and and calculate the value of the output. What would that thread need to do?
It would need to search for the row vector for its corresponding sub vector.
Right.
This
So if
search
I
might
assign a
take a little
thread,
bit of time.
right, exactly. So if I assign a thread here to row 0, for example, so if I assign to output element 0, this thread needs to go through the non-zeros in row 0 and multiply them with the corresponding elements in the input vector. So this thread has to go and find all the non-zeros in row 0, which means it'll have to do a search through this array, right? And
But
here,
it's
I
sorted.
might be lucky and the array is sorted, but the COO format doesn't really tell me this array has to be sorted. These non-zeros could be in any order. So I might actually have to do a linear search through the entire array to find the element that corresponds to the row that I'm interested in. So this is why the COO format does not really make it easy for me to assign a thread to every output element and loop through the corresponding row. And this is one of the things I meant by accessibility. Different formats make it easier to access different things. Okay, what does the COO format make easy for me to do?
Assign a thread to each non-zero vector.
Right,
non-zero
exactly.
element.
I can assign a thread to each non-zero element in the matrix. Okay, I assign a thread to each non-zero element in the matrix. So the kind of the most sensible parallelization approach is to assign a thread for every non-zero element in the matrix. Okay, and what that looks like down here is that I assign a thread to every value in the value array. Okay, so that's, I think somebody had mentioned that at the beginning, but I just wanted to emphasize logically what was going on. Logically, what we're doing is we're assigning a thread to every non-zero in the matrix, right? Physically, what happens is we assign a thread to every element in the non-zero array, in the values array. Okay, so we assign a thread to every element in we can assign a thread to every element in the matrix, and that thread, you know, can easily find its corresponding row and column index. And once the thread knows its row and column index, what can it do?
It goes back to the row and takes the corresponding vector element.
Right. So thread one, this thread, for example, knows that it's responsible for the element at row 0 and column 0. So it finds the input value at the corresponding row and then goes and updates the output value at the corresponding column. So to make it more clear, for example, this thread here is responsible for, this thread here is responsible for this non-zero. So it comes, it says, oh, well, I'm responsible for the element at row 2 and column 1. So I will load the input value corresponding to my column index. So I'll load the input value corresponding to that has the index 1, which in this case is 1 over here, and then I will multiply that with my non-zero, and then I will store the result at the index of the corresponding row. Okay. Now the problem with this approach is that I can have multiple threads updating the same. The threads that are processing at non-zeros in the same row will end up updating the same output value. Okay. So what I will need is since I have multiple threads that are writing to the same output value, I will need something like atomic operation. Okay, so this is, if I use the COO format, this is how I would have to implement SPMV. I would assign a thread to every non-zero. Every thread will be responsible for one element. Okay, it'll get the corresponding value. It'll get the input value corresponding to its column index, and then it'll store at the output value corresponding to its row index. Okay, let's implement this. And because we have multiple threads writing to the same output value, we'll do atomic operation. Let's go and implement this and see how it works. So I'm going to switch to my code over here. Here I've set up the code to where I have a matrix in the COO format. I allocate copy to the GPU, and then I call the GPU kernel, and the number of threads I give it corresponds to the number of non-zeros in the matrix, and then I copy back the output vector and I free the data. So let's go and work on the code itself. So I have my COO matrix, okay, and I have my input vector and I have my output vector. So first thing is each thread is going to be assigned to a different non-zero element. So the thread first needs to figure out the index of the non-zero element in these arrays that it's responsible for. Okay, so I will find the global index of the thread. I'll write unsigned int I is equal to block index.x times block dim.x plus thread index.x. Okay. So I over here is going to be the index of the non-zero element. Okay, so it's going to be the index that I will use to index the value array, the column array, and the row array. Okay, now one thing I need to make sure of is I need to make sure that I am within bounds. So what do I have? How could I be out of bounds? What do I need to compare I to make sure that it's within bounds? Well, I need to make sure that I don't have any threads out here. I just make sure that I is less than the total number of non-zeros in the matrix. All right, if I is less than the total number of non-zeros, so the COO matrix has a field over here which is non-zeros. Okay. So now that I've done my boundary check, now I know that the thread processes a valid non-zero. So now I can process the element at that thread. So what do I need to do for each element? Well, I have to find its row. I have to load its row index. I'm gonna have to find its column. I'm gonna have to load its column index. I'm gonna have to find its value. So I load the value from here. And then I'm gonna need to get the element that corresponds to the column index from the input vector, multiply, and then add the result to the element at the corresponding, the output vector at the corresponding row index. Okay. Find the row. So the row is going to be in the row array of the COO representation. So I'm gonna get my COO matrix, and in my COO matrix, I'm gonna have a row indexes field, okay, and this row indexes field is indexed by what? It's going to be indexed by I, okay, because I is the index of the non-zero. Okay, similarly, I'm going to get my column value. So my COO matrix is also going to have a field called all indexes, okay, and this field is going to be also going to be indexed with I to get the corresponding column index, okay? And I'm also going to load the value. So the value is a floating point number. So I'm going to load the value, and the value is also going to be at COO matrix dot values, and I will access it with the element I. So now I have the row and the column and the value that the thread is responsible. Now what do I need to do? Well, I need to multiply the value with the input element at the column index and add it to the output element at the row index. Okay. What I'm going to do is I want to do out vector of row, and I want to add to it in vector of column times the value. This is what I would like to do. Now, what's the problem if I just do it this way?
Race condition.
Right, I have a race condition. So what can I do to avoid the race condition?
Atomic add.
Right, atomic add. So instead of doing this, I will do atomic add. I'll give it the address of the value I'm adding to, and I will give it the value that I would like to add. Okay, so this is a COO. This is how we would implement sparse matrix vector multiplication in COO. All right, clear? Any questions? By the way, I apologize. I should have shown you the representation before we implemented this. So here, this shows you how the COO matrix is represented. I have num rows, num columns, num non-zeros, row index, column index, and the values. So these are the different fields that I need in the COO matrix. Okay. All right, let's compile this and run it and verify that it works. So we're going to compile, and then we're going to run. And indeed, it works. And as you can see, we get around 4 times speed up in the kernel. This is also a relatively small matrix that I'm using. So the smaller the matrix, the less speed up you'll get. But still, 4 times is substantial. Of course, if you include all the copy time, right, the GPU is not doing very well. But that's because, again, it's a small matrix. And then also, you know, because sparse matrix vector multiplication has low data reuse, you can expect that the GPU performance is not going to be as substantial as if you have something that has a lot of data reuse. Okay, so we already talked about what's bad in doing sparse matrix vector multiplication this way. We have these atomic operations, but what's good about doing it this way?
We only do the number of necessary operations, like we ignore all the non-zeros since the format is
Okay, so sure, we're only going to load kind of do a number necessary operations. Actually, in most formats, we do the only necessary operation. In some cases, we might have to store some of the zeros and do some unnecessary operations, but in most cases, we don't. How's our memory access pattern here to the matrix?
It's coalesced.
Right. Every thread is when we access the value array, when we access the column array, when we access the row array, our accesses are all going to be coalesced. Okay. So we actually have good coalescing behavior for the matrix. Okay. Of course, the vectors are not going to be as coalesced. The input vector is not going to be as coalesced. And the output vectors, we're using atomic operations, okay? But at least when we access the matrix, the accesses are coalesced. So this is the code that we wrote. I'm going to talk about various advantages of doing this, but first let me kind of show you how we can see the accesses are coalesced. So here, I corresponds to the thread index. So every consecutive thread has a consecutive I value, and you can see how when we're accessing a row index and our column index and our values, we have nice coalescing behavior. Okay. Any questions about the code? Okay, so let's talk about the trade-offs of the COO format. So first of all, we mentioned some advantages and disadvantages. Let's kind of recap them. So first, the advantages of the storage formats. Remember, we talked about different metrics by which we talk about advantages and disadvantages. One of them was space efficiency. Another one was the flexibility, how easy it is to add and remove elements from the format. Another one was accessibility. What does the format make it easy for you to access? Another one was coalescing, and another one was control divergence. Okay, so for the COO format, okay, how does the COO format do in terms of flexibility, easy of adding and removing elements? Well, if we go back to look at the storage format itself, here I can easily kind of reorder the elements. I can easily, if I want to add elements, it's quite easy because I can just add stuff at the end of this array. Okay, so the COO format actually makes it easy for me to add elements. Removing elements is a little bit more difficult because if I want to remove and I want to shift everything, that's quite expensive. But sometimes if you remove, you can just replace this with some kind of sentential value that tells you that, okay, this value here is not valid. But the COO format makes it easy for me to add elements. Okay, so it gives me that flexibility. What about accessibility? What does the COO format make easy for me to access? If we go back and look at this over here, what does the COO format make easy for me to access?
The rows and the columns of the non-zero elements.
Right, so given a non-zero element, it's easy for me to find the row and the column for that non-zero element. The COO format makes it easy for me to find the row and the column of a specific non-zero element, which makes it easy for me to parallelize across non-zero elements. Because if I assign a thread to every non-zero element, then I can easily go and find its row and column. So that's accessibility. What about memory coalescing? How does it do on memory coalescing? Like we said, the accesses are nice and coalesced. What about control divergence? How does COO with SPMV do on control divergence?
Does not have control divergence.
Right, there's no control divergence because every thread does the same amount of work. Every thread processes one non-zero value. Okay, so if we go and talk about the advantages of COO, we saw that we have the flexibility it has good flexibility because we can easily add new elements. Okay, and also the non-zeros can be stored in any order. In terms of accessibility, it makes, given a non-zero, it makes it easy for us to find the row and the column. This allows us to easily parallelize across non-zeros. We also see that SPMV COO has coalesced memory accesses to the matrix. And we also have that SPMV COO does not have control divergence. Okay, what about the disadvantages? What were the disadvantages of the COO format? What did the COO format make hard for us to do?
Accessing and using the coordinates.
Right, exactly.
To do
So,
search.
right, exactly. So we said that if we want to go through all the elements of a single row, right? When we came, we said, hey, you know, why don't we try to parallelize? Why don't we try to parallelize by assigning a thread to every output element and having that thread compute the input rows? Well, we weren't able to do that because it's not easy for us to find all the non-zeros for a particular row. So if we look at accessibility, given a row or a column, it's hard for us to find all the non-zeros. We need to perform a search. Okay, and the other disadvantage is that because we cannot do this, we have to use atomic operations. So these are some of the advantages and disadvantages of COO. So to address the disadvantages here, to avoid doing atomic operations, to be able to assign a thread to every output element and go through the corresponding row values, there's another format, which is the compressed sparse row format. So if I have if my matrix looked like this is the same matrix we had before. This time what I've done is I've colored all the elements in the same row, the same color. The way the compressed sparse row format works is that we're going to store the non-zeros in the same row adjacent to each other, and we're just going to store an index to the first element of each row. So here for our values, we're going to have the non-zeros in the first row next to each other, the non-zeros in the next row next to each other, the non-zeros in the third row next to each other, etc. For each of these values, we're going to have the corresponding column index. So here, 1 is at column 0, 7 is at column 1, so we have 0, 1. Over here, 5, 3, and 9 are at columns 0, 2, and 3, so that's why we have 0, 2, and 3 over here. 2 and 8 are at columns 1 and 2, so we're going to have 1 and 2 over here. And then what we're going to do is we're going to store for each row where the non-zeros of that row begin. So we're going to call this the row pointers array. So we're not going to have a row index array like we had before, where for every non-zero we had the row index. Instead, we're going to have a row pointers array that stores, it doesn't really store a pointer, it stores an index. It's going to store the index at which the non-zeros of each row begin. So here, the non-zeros of the first row begin at index 0. The non-zeros of the second row begin at index 2, so we store 2 over here. The non-zeros of the third row begin at index 5, so we're going to store a 5 over here, etc. So now let's say that we wanted to use this format to implement SPMV. How would we implement SPMV with this format?
One thread per row?
Right, exactly. We can have one thread for every output element that loops through the row corresponding to the output element and does the computation. So we're going to assign one thread to loop over each input row sequentially and update the corresponding output element. All right. Now, well, this looks like this. Okay, we have a thread for each that starts at the first non-zero of each row. Now, if you look at what this looks like down here when we're going through our values array, we're going to have the first thread starting here, the second thread starting here, the third thread starting here, and then the fourth thread starting here. Now, on the next iteration, this fourth thread is done, so it's finished working. It's going to wait for the rest. The second thread, comes here. Third thread comes here. Fourth thread comes here, right? On the next, they each go to the second non-zero element in the matrix. On the next iteration, the first and the third thread are done. There's only the second thread remaining. So all these guys are done. They're waiting for this thread to finish, and this thread goes to the next element of the matrix, and then we are done. Okay. So what are the advantages and disadvantages here?
We have controlled divergence as a disadvantage.
Right. So one of the advantages is that we have control divergence. Every thread has a different amount of work that it needs to do. So we have control divergence. What's another disadvantage?
Memory accesses are not coalesced.
Right. When we're going through this array, the memory accesses are not coalesced. What's the advantage?
There's
There are
no
no atomic
atomic
operations.
Right. We don't have
Well,
atomic
but we
operations.
can load
Every
to
thread.
shared memory, right?
Sorry.
I mean, we can load for every thread, we can load to shared memory, right?
What do we want to load to shared memory?
I mean, the array of the value.
So how does loading the array of values to shared memory help me?
So I don't access for in every iteration I access the global memory.
So do I
Is
have
there
data
such?
Do I have data reuse here?
Well, if we can use for every thread, it can load like for every thread loads one value instead
Right.
of iterating. I mean,
I see what you're getting at. So what you're saying is you want to use shared memory so that you load in a coalesced way and then access in an uncoalesced way from shared memory. Is that what you're saying?
yes, it's somehow.
Yeah. So you can kind of do that for very large matrices. You don't really have a guarantee to fit in shared memory. So that might be a challenge. Okay. Also, there's other ways to improve coalescing other than using shared memory. So we're going to use different way to improve coalescing. Okay. But also in general, shared memory is not very effective for SPMV because you don't have data reuse. Every element in the matrix is used exactly once. So yes, you can use shared memory to improve the coalescing behavior, but there's better ways to improve the coalescing behavior by rearranging the data. Okay.
Professor,
Yes.
is there also as a disadvantage, can we consider that we're not maximizing the number of threads running that could run
Yes, you can
eventually?
say that. So we have less parallelism here. We have less parallelism. Now, depending on how big our matrix is, that may or may not be a problem. Okay, so if our matrix is not that big, we're creating fewer threads, so we're not fully utilizing the GPU. If our matrix is huge, then we may not have a problem there. But still, we have control divergence. So some threads will finish before others, and we'll have to wait for the slowest threads to finish. So we will have underutilization of our GPU at some point. Okay, let's go and implement this and see how well it performs. So I'm going to I'll leave my COO implementation, and I'm going to go into my CSR implementation. Over here, just to show you, I have a CSR matrix struct defined. I have num rows, num columns, number of non-zeros, and I have the row pointers, the column index, and the values. Okay, when I come down and I want to implement my SPMV kernel, we said what are we gonna assign every thread to?
Each output element.
So every thread is going to be assigned to an output element and the corresponding row for that output element. So the thread index is also going to be the row index. So here I will write unsigned int row is equal to thread index, equal to thread index dot x, thread index dot x, excuse me, block index dot x times block dim dot x plus thread index dot x. What does my boundary check compare to? if I'm assigning a thread to every output element, what does my boundary check compare to make sure my threads are in bounds?
Size of row pointers.
Right, so the number of rows basically. So I'm gonna row pointers is actually an extra element that gives me the total number of elements, so that for the last row I know where it ends. Okay, because every row pointer, the next row pointer tells me where the previous row pointer ends.
Hello.
So then for a boundary check, we need to make sure that the thread is processing a row that is within bounds. So we will do if row is less than CSR matrix dot num rows. Okay. And then once we have the thread, once the thread has figured out what row it's responsible for, what this thread needs to do is that it needs to go and it needs to find the non-zeros for that row, and then it needs to go through them and loop through them one at a time, stopping at the last value. So how does the thread figure out where its non-zeros start? Well, it's going to use the row pointers array. Okay, so what I will do is each thread is going to loop through the non-zeros inside of its row. It's going to start at row pointers of row, right? So thread 0 will start at the value at row pointers of 0. Thread 1 will start at the value at row pointers of 1, etc. So here the thread will start at Csr matrix dot row pointers of row. Okay, where does it stop? So it starts here and then it loops. Where does it stop? Well, it stops at the row pointers of the next value. Right, it's going to stop at the row pointers of the next value. So here we will stop at csr.row pointers of row plus 1. Okay, and this is why we need to have one additional element at the end, so that the very last thread knows where that it needs to stop. So this last element will tell me the total number of non-zeros in the matrix. It also tells me where the last thread stops. So for I is equal to CSR matrix dot row pointers of row, I is less than CSR matrix dot row pointers of row plus 1 plus I. And now what we would like to do is for each one of these values, we're going to get the column index, get the value, okay, and multiply the value with the input element at the corresponding column index. Okay, so how do we get the value at the column index? Let's first get the column index. We're going to get unsigned int call is equal to, we're going to use the column indexes array, and we're going to index it with I, which is the counter in this loop that's going from the beginning of the non-zeros in the loop until the end of the beginning of the non-zeros of the row till the end of the non-zeros of the row, and then we're going to write float value. We're going to get the value we're going to get from the values array. So we're going to write CSR matrix dot values of I. Okay, and now what we would like to do is we want to increment the value at we want to increment the element that we're responsible for by the non-zero times the input element of the corresponding column index. We're going to do out vector of row plus equals the value times the in vector of column. Okay. Now, since out vector here is in global memory, to avoid, well, first of all, since this thread is the only thread that's going to write to its out vector, since each thread owns its own element in the output vector, we don't need an atomic operation here. Okay, because every thread owns its output element, and because of that, we also don't need to read and write from global memory on every iteration. We can simply initialize a counter outside the loop. We can or an accumulator outside the loop. Okay, and then we can instead of having out vector of row here, we can increment the accumulator, and then after that we can store the accumulator at out vector of row. Okay, so this is the code for doing SVMV using the CSR format. Any questions about this?
Professor, I want to ask, why don't we assign each element a thread? Why don't we assign for each a thread for each element in the matrix?
You mean for why don't we assign a thread for each element in the CSR matrix?
Yes. So why do we perform this loop for this for loop?
So great question. Let's assume that we wanted to implement the previous approach, which was the approach we implemented with COO. Let's assume we want to implement that with CSR. So let's say I wanted, with the CSR format, to assign a thread for every non-zero element and make that thread responsible for that non-zero element. Would it work with CSR?
I just need to keep track of the row pointers for each element and the value.
So the thread if I assign a thread to every value here, the thread can find out what its value is, what its column index is, but how does it know what its row is? Right? If a thread with index 3, for example, knows that it's responsible for this value, okay, the thread with index 3 happens to also have the value 3. It knows that it's responsible for this column 2. But how can it find out what its row index is? It's going to have to come and search inside of this row pointers array for which row contains the non-zero at index 3. In this case, it would be here because 3 is in between 2 and 5. So it'd have to do some kind of binary search inside of this row pointers array to go and figure out what its row index is. And that is why the CSR representation makes it easy to parallelize across rows or across output elements, but it doesn't make it easy to parallelize across non-zero. Because given a row, we can go and find the non-zeros for that row, but given a non-zero, it's hard for us to go and find the corresponding row. We have to do a search. So this is one of the trade-offs of the CSR format. And I'll talk more about trade-offs, but let me first run the code and show you the performance. So let's close. And we're now going to compile the CSR code, and we're going to run the CSR code. And as you can see, it actually has worse performance because of the atomics, okay? And because of the poor coalescing. Now, in this particular case, it has poor performance, okay? In other cases, depending on the matrix, depending on the dimensions, the CSR might have better performance than the COO. Okay, but in this particular case, for this particular matrix, CSR actually performed poorer than COO with atomics, because the performance penalty that I got from having poor coalescing and poor divergence was worse than the performance penalty that I got, poor coalescing and high control divergence was worse than the performance penalty that I got from the atomic operation. Okay, clear? Any questions about that? You will notice something though. You'll notice that the copy time to the GPU and back, the copy time to the GPU is lower than the copy time to the GPU for COO. Why is that?
We had row before as opposed to row pointers now, which is smaller.
Right, exactly. So it takes me less time to copy the CSR matrix to the GPU than it takes me to copy the COO matrix to the GPU. Okay, and the reason is that the CSR matrix does not have a row index array, it just has a row pointers array, which is much smaller. So the CSR matrix is actually more space efficient than the COO matrix. Okay, so let's compare CSR and COO based on the different metrics that we talked about. So in terms of space efficiency, what's better, CSR or COO?
CSR.
CSR, right? In terms of flexibility, so the ease of adding elements to the matrix, which one is better?
CSR also.
COO.
Adding elements, right?
CSR.
COO is better because with COO I don't have an order, right? I can simply just add elements at the end of the arrays. Whereas here, if I wanted to add an element to column 3 or if I want to add an element to row this second row or the third row over here, what would I need to do?
Increment all the elements after the
Right,
row
exactly.
pointers.
So all the elements in the same row need to be next to each other. So if I want to add an element to a particular row, I'm going to have to shift all the elements in their later rows, and I'm going to have to go and increment all the row pointers for the later rows. So in terms of flexibility, in terms of space efficiency, CSR is better. But in terms of flexibility, the ease of adding things, COO is actually better. Okay. What about accessibility? What does COO make easy to access? What does CSR make easy to access?
COO makes easy to access
CO.
any output thread, whereas CSR makes it easy to access any input thread.
No, not output.
Oh, no.
Well, if by input you mean the matrix, then sure. So CSR makes it easy for me to access. Given a row, it's easy to find the non-zeros of that row. So, and that makes it easy to parallelize across rows. COO makes it easy to do the following. Given a non-zero, find the row and the column for that non-zero. So COO makes it easy to parallelize across non-zero. Okay, that's accessibility. What about coalescing?
COO is more memory coalesced than
Right,
CSR.
COO has better coalescing. What about control divergence?
COO is better.
Right, COO is better. And what about synchronization, having to use atomics and things?
CSR is better.
CSR is better, exactly.
Professor,
So if we go back to our trade-offs, yes, question?
for CSR, aren't the memory writes coalesced?
You mean the right to the output vector? Yes, they are.
Oh,
Yes,
okay.
you're absolutely right. So you're absolutely right. CSR makes coalescing the writes to the output. CSR helps you coalesce the writes to the output, whereas with COO you have to use atomics there. But COO makes it easier to coalesce the inputs. And since the input matrix is larger than the output vector, usually that's what dominates your memory access, and that is why when talking about coalescing, we've been focusing on the matrix because it's larger.
Okay,
So
thank
the
you.
advantages of CSR are that it has better space efficiency, it has better for accessibility. It allows us, given a row, to find all the non-zeros, and then SPMV CSR avoids atomics because every thread owns its output. But the disadvantage is that it's hard to add new elements to the matrix, and then for accessibility, given a non-zero, it's hard to find a row. Given a column, it's hard to find all the non-zeros for that column. And then SPMV CSR axes are not coalesced, and SPMV CSR has control divergence. Okay. So one thing here to note is I kind of sneak this in here. So given a column, it's hard to find all the non-zeros for that column. Okay, so CSR, given a row, it helps me find the non-zeros in that row. But if I want to, for example, do a column traversal down a column, I cannot do that with CSR. So there's actually a transpose of CSR, which is, well, not a transpose of CSR, but kind of the other version of CSR, which is compressed sparse column. And CSC is like CSR, but it groups non-zeros by column as opposed to by row. So SPMV doesn't require this, but if I have some other computation that requires me to loop through the columns of a matrix, okay, in this case, CSC would put the non-zeros of the first column next to each other, followed by the non-zero of the second column next to each other, followed by the non-zero of the third column next to each other, etc. So CSC would have similar advantages and disadvantages to CSR, except for accessibility. CSC makes it easy to access the non-zeros of a column given a column index, whereas CSR makes it easy to access the non-zeros of a row given a row index. Okay? Now, it would be nice if we go back to these trade-offs, it would be nice if we can avoid the atomics, which is what CSR gives us, but at the same time, have a better memory access pattern, so where our access pattern is coalesced, and also be able to reduce our control divergence. So it would be nice if we could have the best of both worlds. And for this reason, what we will, this lecture is to be continued. Okay, next time what we will do is we will look at other storage formats that allow us to improve coalescing and also reduce control divergence. In particular, we're going to look at the LPAC format or ELL, which helps us improve coalescing compared to CSR. And we will also look at the jagged diagonal storage format or JDS, which will help us reduce control divergence. Okay? Any final questions before we end?
Professor,
Yes.
in all those formats, if you have a row or a column of complete zeros, can you collapse it or no? Do they offer that or no?
Well, it depends. It depends. In COO, if you have a row or a column that doesn't have any zeros, okay. One question is why should that be in your matrix in the first place? But in some cases, yes, you could run into a situation where one of your columns or rows all have zeros. In COO, if you have a situation like that, then you won't pay anything for that, right? Because COO will only store the non-zero with its commutative row index. In CSR, if you have a row with all zeros, you will still need to have an element for it inside of the row pointers array, but you wouldn't have any values for it inside of the values of the column index arrays. But we will see in some of these other formats, even if a row was all zeros, we might still need to have some data allocated for it. So we'll take a look at that next.
Okay, thank you.
Right. Yeah, you're welcome. Any other questions? Okay, if not, then you can read more about what we covered today in chapter 10 of the textbook, particularly these sections. And that's all for today, and I will see you next time. Bye, everyone.